Welcome to another session of physical sciences, specifically chemistry and specifically chemical equilibrium. The last time we worked and we learned about Le Chatelier's principle, and we spoke about Le Chatelier's principle. We looked at the factors, and we also looked at how to answer these questions on Le Chatelier's, when there's disturbances, how to answer these questions. And we said that we have the SRFE way of answering it. In this session, I would like us to look at graphs. I specifically want us to look at concentration graphs. And this concentration graphs is now linked to Le Chatelier's principle. When a stress is applied to a closed system in a state of chemical equilibrium, remember this stress must be applied where there's chemical equilibrium, what changes will be seen on the graph of a concentration versus time graph? So we've seen the rate graphs a little earlier. We spoke about the changes in the rate of your forward and your reverse reaction. But whilst we were looking at the rate graphs, I also brought up for the example of the production of ammonia, I also showed you how it will look if we look at the concentration of the different substances that are used. So this session will basically focus on how does the concentration time graphs look. We're going to investigate the changes to the concentration versus time graphs. And a closed container contains a mixture of hydrogen, nitrogen, and ammonia at this 350 Kelvin at a specific temperature. The reaction mixture has reached a state of chemical equilibrium. Now, we have in front of us the concentration graph that I showed to you before. Remember what we said? This is the nitrogen, the purple line. We have a yellow line, which is the hydrogen gas, and then the ammonia is the red one. Just remember, this is a concentration graph, so it will look at the different concentrations of the substances. The concentration of the reactants and the products at this point from the white line onward, these concentrations are constant. Remember, I said to you last time, we don't say the concentrations are the same because it's not necessarily the same. It's actually never really the same. But the concentration remains constant at that state of chemical equilibrium. The factors that will disturb equilibrium, we've learned about them according to Le Chatelier. We've got concentration, we have pressure in the case of gases, and then we will look at the change in temperature, how that will affect the concentrations and how it will affect the concentration time graphs. A closed container contains a mixture of nitrogen, hydrogen, and ammonia at 350 Kelvin. The reaction mixture has reached a state of chemical equilibrium. Remember what I said last time? There must be a state of chemical equilibrium, else the equilibrium cannot be disturbed. So in this case, the concentration of hydrogen is increased. Now, what you should think about is the disturbance is an increase in hydrogen gas. When we look at the graph in front of us, firstly, I need you to note that the fact that we have parallel or horizontal lines here, you need to understand that at that point where my nitrogen, my hydrogen, and my ammonia has got horizontal lines horizontal to the time axis, it means at that point the system is in chemical equilibrium. Then comes the disturbance. And what is the disturbance? An increase in hydrogen. So our hydrogen concentration increases. So what will happen to the rest of the system? Let's see what Schrift shows us. There's an increase in the hydrogen concentration. What did Le Chatelier say? That the system will react to decrease the hydrogen gas. And for it to decrease the hydrogen gas, it must use up the hydrogen gas. And in using up the hydrogen gas, it actually means that the hydrogen and nitrogen must now favor the forward reaction. And when the forward reaction is favored, we will have less of N2 because the N2 plus the H2 has now increased the concentration of the ammonia. Now we're back at the graph, the concentration versus time graph. Remember what we said. We said that the disturbance was an increase in hydrogen gas. What did the system do? The system tried to decrease the hydrogen gas. And in decreasing the hydrogen gas, the forward reaction was favored. When the forward reaction was favored, the concentration of the ammonia gas was increased. So we have a vertical line up to show the disturbance, and we use a vertical line up for an increase in concentration. Then we see that the product is now increasing with a curved line, and the nitrogen gas that's now been used with the hydrogen to use the hydrogen gas up, the nitrogen will now decrease, and ultimately hydrogen will also decrease, and it will go into a new state where we have horizontal lines that's parallel, and that means that the concentration here is now constant. Remember, we do not say the concentration is the same, we say that the concentration is constant. Right, that line there just shows us that from there onward, our concentration is the same. Meaning, this is the new equilibrium that's being reinstated according to Le Chatelier. Now, we're going to just quickly summarize what just happened on the concentration graph when one of the concentrations is increased or decreased. Specifically, we looked at an increase in concentration. When we have an increase in concentration, the feature on your concentration time graphs is there's one vertical line. And because it was an increase, that one vertical line for hydrogen gas went up because it showed increase. The other two was affected by the response of Le Chatelier, and they were more curved lines. If we would have worked with a decrease in concentration, we would have had one vertical line, but that one vertical line would have been down. We've now looked at the disturbance of the concentration of one of our reactants, and we looked at how that is shown on a concentration time graph after the disturbance to reinstate the equilibrium. Now we're going to look at the next one. We're going to look at pressure. Remember, pressure is we only get pressure in gases. And whenever I say the word pressure, you should think volume. So we still have the nitrogen, hydrogen, and ammonia gas at the same temperature there. The reaction is at a state of chemical equilibrium, and the disturbance now is the volume of the container is decreased. What does the volume, if we decrease the volume, what does that do? Right, a decrease in volume will now increase the pressure. Remember, our volume is inversely proportional to pressure, or our pressure is inversely proportional to volume. So the decrease in volume leads to an increase in pressure and the increase in concentration for all the gases. So whilst the volume was decreased, the pressure was increased, and the concentration of all the gases was increased for that specific volume. Right. Here we have our concentration time graph, and remember we have concentrations of ammonia, nitrogen, and hydrogen. First thing here is, when we look at the disturbance of pressure, you will see there's a spike for each one of them. Just want to take you back. Remember we said there will be an increase in pressure, and that will increase the concentration for all gases. So it increases the nitrogen, the hydrogen, the yellow one, and it increases the ammonia. What do we know about an increase in pressure? The stress is an increase in pressure, and according to Le Chatelier, the system will react to try to decrease the pressure by decreasing the number of moles. When we want to go for the number of moles, remember we're working with pressure. We have 2 moles on the right-hand side and 4 moles on the left-hand side. So if we want to decrease the number of moles, the reaction that produces less number of moles will be favored. In this case, it is the forward reaction. So what will happen if the forward reaction is favored? It basically means that the concentration of nitrogen and hydrogen will decrease, and the concentration of ammonia will increase. So the nitrogen and hydrogen will decrease, and the ammonia will increase. So here we show the disturbance, our vertical lines. The pressure was increased, so all the vertical lines were up. And now, after equilibrium, we have more NH3, we have less N2, and even less H2. Remember I said to you earlier, there's more of a decline in the hydrogen gas because our nitrogen to hydrogen is in a ratio of 1:3 in this reaction. Right. When we look at the stress of change in pressure, the feature on the concentration time graphs, there's always many vertical lines. If the pressure is increased, those vertical lines will be up. If the pressure is decreased, the vertical lines will be down. And then only we show the effect of equilibrium. That brings us to the last one, where we're going to look at the effect of temperature, and we're specifically going to look at the effect of temperature in a closed system that is in a state of chemical equilibrium. We will look at the reaction of hydrogen, nitrogen, and ammonia at 350 Kelvin. The reaction mixture has reached a state of chemical equilibrium, and we want to now work out what will happen if the temperature is increased. Now we know, firstly, when we talk about temperature, we first need to go look at exo and endothermic reaction, because an increase in temperature will always favor the endothermic reaction. So we need to go see which reaction here is endothermic, and we see that the forward reaction is exothermic, meaning that the reverse reaction is endothermic. An increase in temperature will then favor the reverse reaction, which in this case is endothermic. Or we can say an increase in temperature favors the endothermic reaction, which in this case is the reverse reaction. What is the stress? According to Le Chatelier, it's an increase in temperature. The system will react to decrease the temperature by favoring the endothermic reaction. In this case, our endothermic reaction is the reverse reaction, meaning we will have less of NH3 and more of N2 and H2. How will that look on our graph? On our graph, we will see our NH is used up, our N2 is becoming more, and our H2 also becomes more. Remember, we have a 1:3 ratio. But what you need to note here is we only have curved lines when we look at a temperature as a disturbance. So, the feature on your concentration versus time graph is all lines are curved. We will see that an increase in temperature will show that the concentration of your endothermic reaction increases. Decrease in temperature, the concentration of your products of your exothermic reaction will increase. And that brings us to the lovely part of the day. We're going to take a break, and I'll see you soon.